Thank you all for coming. Like I said, I'm Logan Ledbetter, and in the summer I work with Flames Electric, and we were contracted through a third party to upgrade a plastics line here locally in Evansville. A little bit about Planers. We design industrial electric motors, and we manufacture and repair those motors, as well as design the control systems and drives that run those motors. More recently, we actually have developed a systems integration group, which actually takes on projects like this one, where we take a company from outside of Flanders and they come to us with contract work, and we go on site and decide what needs to be done. A little bit about our systems integration group. We determine the specific hardware, so that means the speed of logic for anything that's control-based, as well as the voltage and current that's used on any of these devices. We also ensure that all parts of the program are compatible, so that means any versions of specific programs that we use, we make sure that those all mesh together so that when we go to install, we don't have problems with these two programs running into each other and they all work fluidly. We also strive to meet all design goals. That is to say that they come to us with a contract and they say we need this, 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 and this, and we make sure all of that is met, and we also tell them when we run into problems that may cause them not to be able to meet these design aspects, and come up with a solution that may also benefit them. And then after all that's done, when the project is complete, we actually go on site and commission the project. This means in many cases, we install the hardware and the software, and then we test it all to make sure it's running properly. Our line upgrade team was Gilberto Escobedo. He was our project lead, so he kept us on task. He decided all of our due dates. He also made sure that we got paid, and decided all of the requisitions that were needed for this. Logan Storer was actually the head on the design team. He took care of all the PLC programming. The PLC is a programmable logic controller. You use ladder logic to decide many things through control. They get a set of inputs, and from those inputs they determine the correct outputs to send out to the system. And he was in charge of upgrading the system from General Electric or GE to an Allen Bradley system. And then myself, I was in charge of the HMI programming. HMI is a human-machine interface. This means that you come up to a screen and you punch in what you need to be done, and the inputs and outputs from the PLC are changed based on those things. And I also was converting that from a GE program to an Allen Bradley program. And then Nick Brower was our drives designer. He designed all of the drives programming that would go into the new drives that we designed for this cabinet, or for this project. And he made sure that they all work properly. Project overview, as I said before, we worked on at a local plastics company. This was not designed by Flanders. They have their own specific plastics lines, and we went on site to upgrade them from outdated GE electronics and hardware to new Allen Bradley hardware and software. The current hardware was slow and outdated, so they needed that upgraded to prevent problems on the line, and with the hardware, the software also had to be upgraded. Another benefit of this would be that it would help eliminate some of the stock in their storeroom that they use for repair on this project, as some of the other lines had already been upgraded to Allen Bradley. So they didn't have to stock nearly as many parts. It also would allow for cross-training from other members of the line, so that in the case of illness or vacation, other members from within the plant could be brought to this line to work, and as opposed to needing special training to work on this line as it was on a different system. This is a sample of the line that we worked on. For proprietary reasons, the company has chosen to stay anonymous, so this is not their exact line, but it's very similar to this. On the far left, the two-cylinder looking things are hoppers. In those hoppers, it would hold different types of plastic pellets. Those plastic pellets, designed for different types of plastic sheeting that would be used, we fed into the machine below it, which is the extruder. This heats the plastic pellets to a certain temperature where they're extruded out the front by an auger. This auger pushes the plastic out into the rollers that you can see just beyond that. The rollers then press that plastic into its designated shape, where they're then sent off to the heaters, which are after that. The heaters then heat the plastic back up so that it can be actually pressed into its final shape before it goes off to the shear and stacker. The shear actually is after that, and it cuts these sheets to their designated length that's specified by their customer. And after that, it's passed on to the stacker, which picks each of these sheets up and stacks it in a box or a crate for shipping later. All right, so the hardware upgrades, as I mentioned before, we were going from GE or General Electric to an Allen Bradley system. This included the upgrade of their programmable logic controllers, or PLCs. The Allen Bradley was already installed in other parts of the plant, as I said before, so they chose to go with that on this project. The team on site was very familiar with this type of hardware, so it was also easy for them to install it as well as work on it later. The input-output, or I/O devices that would be used, would be kept as the GE I/O devices. They actually developed a specific device called a Genius Bus, which can convert the GE I/O into Allen Bradley I/O, so that there's not any confusion from the I/O modules to the PLC itself for control purposes. In regards to the software, the GE was upgraded from Prophecy, which is their version of ladder logic, to an RS Logic file, which is Allen Bradley's version of ladder logic. The ladder logics the files were actually sent to a third party offsite. I believe this company is in Utah, and from them, that's all they do. They convert files from one version to another. And from them, in about 2 weeks, we got back a version of these files that was roughly 75% complete and ready for install. What was needed was the new component tags that would be added in the PLC, so they could recognize new aspects of the line that did not exist before. The Genius Bus conversion, as I mentioned before, that helps to convert the I/O from GE to Allen Bradley I/O, as well as any of the unit conversions that occur as a result of this change. In the HMI, the GE program was called Simplicity, and this is what the screens were all programmed in before. And this was all converted into Rockwell Factory Talk. And a little bit about HMIs, the way that they work is you have a section of buttons on a screen, and each of these buttons is actually linked to a set of what are called tags. And these tags each hold a bit of information, whether it be a Boolean tag for simple logic like on-off, or an analog tag for something that is like a heater or a pressure gauge. These tags all hold this type of data, and when you press one of these buttons, it corresponds to a specific tag. And this tag is then fed through the HMI into the PLC, and then corresponds to a set of I/O that the PLC then changes and sends back out as outputs to display or change something in the line. For this conversion, a list of currently used screens on the HMI that existed already was sent to us as a reference, and then in the Rockwell Factory Talk program, we actually redesigned every single screen from scratch. So we put in all of the buttons to give them all the same function. However, as I mentioned before, they wanted to be able to cross-train members of their plant on this line. So we were told to make this line look as much as possible like the other lines, but also to keep all the same functions that were currently on this one. Here's a sample of that screen conversion. The left is the Simplicity screen, and on the right is the Allen Bradley Factory Talk. With both of these screens do all of the same functions. You may notice that many of the buttons are the same, just with different colors, but what you also may notice is that there are switches and inputs. Again, they wanted the final design to look as much as possible like other lines in the plant. However, both of these screens actually give all the exact same capabilities. After we finished our design at Flanders, we went on site for installation. All of the components that would be the design files, the data files, were placed on a central server that could be placed in this company's server room. The server was then linked to 5 of these HMI screens through Ethernet cables. And the advantages of this is with the central location for the server, all the files are in the same place. So if you have a problem out on the floor and you need to change a file, you don't have to change it in 5 different computers. You just change it in one, and then it's linked to all 5 of these. Another advantage is there's no additional cabinet needed for the computers that would be installed. As I mentioned, there is a central location for all of these servers, and they already have a spot waiting for us. There's also, and also without the extra client computers that would be running each of these HMIs, we reduce costs because you only have to buy one computer. This is a sample of kind of how that works. The server would then be linked to the HMIs. In this sample, there's only 3, but we did have 5 on this project. And the server can actually link separately to each of these, but all of these are connected back to the server. So what this means is that each of these screens does not actually have to look at the same HMI screen. Each of them can be on something different, but when you change data on one screen, it does correspond to the other screens. With testing, after we finished installing all of these products, the startup was tested from the end of the line back to the beginning. This is because at the beginning we have the extruder which has heaters in it, and if something is wrong there, then we may screw up the entire line. So we started from the end and worked our way back from the stacker and the shear to make sure all of those functions worked properly. Each set of motors and heaters was operated independently for this, which means that we, in the PLC code, we actually set in temporary fail-safes, or e-stops, that would prevent other parts of the line from running, but also not give us an error message and shut everything down. When all the components were tested from reverse to the front and made sure that all of them worked independently properly, we started linking them up again from the end of the line back to the beginning to make sure that the sheets would be fed into each piece properly. So the rollers started working, and we started pushing what was a dummy sheet through the line. This was not heated or cut or anything like that. We just made sure that the sheet would actually feed from each part of the line to the next. And once all of this was done, we actually started up the line, but at a greatly reduced rate. This line usually runs anywhere from 700 to 1200 degrees, and what we started at was roughly 400 degrees. So it was able to push plastic, but it was not in any way that would be dangerous or actually useful to the company. This is a sample of how we tested the drives. On the left is the cabinet which actually holds the drives, and on the right are 2 of the rollers that these drives actually control. Through the HMI, we told these rollers to be turned on, and we had somebody waiting at these drives to make sure that all of the indicators on the drives themselves looked proper and that they were feeding the information that was supposed to be fed to these rollers. This is a sample of the PLC and I/O testing. On the left, we actually have the cabinet which held the PLCs, and on the right is a sample of what the I/O looks like. The 2 lights indicate that the I/O is working and that is connected to the PLC, and that's what we looked for in each of these blocks before we proceeded. And then with the HMI testing, as I mentioned a little bit before on the drives, we actually used the HMI for all of our testing. So instead of going in the code and saying, run this right now, we actually used the HMI and we punched it in on the touchscreen and told it to run this specific function. So that was our way of testing that aspect. A few problems that we ran into during this commissioning. The printer that they used for their line reports actually was not connected. This is because they changed this printer and it was not recognized by our server. So to fix this, we actually went up and we installed the proper drivers for this printer and found the IP address for this printer and connected it directly to the server so that it could print these things. There was also a bit of confusion with the project drawings that we were given. Some of the operators on the line had actually run into problems with a few of the I/O things, and were told to just eliminate them because they were things that were no longer used. So they simply shut the line down and terminated some of the connections on these I/Os that weren't working. We were not informed of that, so when we went to start it up, we were trying to make sure all of these I/O things were working and some of them were not. So that took us a few hours before we actually realized that these aren't supposed to be working and what is happening is proper. We also had 3 Genius buses on this project, and one of them was not inherently bad. It operated properly, but there's a warning light on the front of these Genius buses that let you know that all of the I/O is coming through and is being converted properly. Now, on one of these buses, this warning light continuously blinked at us. So we thought that there was something wrong. So we checked each line of code and each tag in that bus individually and found out that there were no problems. Contacted the company that makes these Genius buses, and they told us that this is a problem that they've run into before, and they sent us a new one that was later installed on the line. Some of the benefits from this project, as I mentioned before, there are fewer parts to stock in their inventory. So this means that when they go to repair this line, they can pull parts that are used in other lines because they're all the same on this one. These new parts are more reliable than the old GE parts, as well as through using the Genius bus, they actually don't have to stock any of the GEIO. Instead of that, whenever one of these blocks goes bad, they can actually replace it with Allen Bradley IO and then just bypass the Genius bus as far as the unit conversion. Another benefit was cross-training. The operators from other lines we brought up to speed very quickly on this line, as it looked like the other lines. They were able to operate it in much the same way. And maintenance also had the same benefit, as they did not have to be cross-trained on this line for different components that were on it as opposed to other lines. There's also a decrease. We were also told by the customer that we have a decrease in downtime since we've upgraded this line. Again, for proprietary reasons, I don't have exact statistics on that. But they've told us that the new software seems to be less buggy and that the hardware doesn't break down as often. So that's an improvement for them. Knowledge that I gained on this project. I had basic knowledge of a lot of ladder logic and things like that from here at USI, but it was not as advanced as what I needed on this project. So through this project, I actually learned a full suite of Allen Bradley software, their drive programming, their ladder logic, and their HMI software. I learned this all through Flanders. They were very helpful in helping me with that. I also learned the diligence of communication. I guess I shouldn't have assumed that just because I sent it in an email once a week that everybody knew exactly what I was doing. It was something that needed to be updated daily or even every few hours as things changed on the project. And that was something that caused me a little bit of havoc in the beginning, but helped me later as I learned that this was something that had to be done. I also learned that things will go wrong. No matter how much you prepare for, how much you design out, when you go to commission or install something on site, there will be something that goes wrong and throws you for a loop a little bit. As engineers, what I've learned is that what we have to do is design as many of these problems out as we can in the beginning, but then be prepared to fix these problems as efficiently as possible when they do show up. So a quick summary of what we did. Flanders was contracted from a local process company to upgrade their line from General Electric or GE to an Allen Bradley system. This would be all of their software, their PLC, their drives, and their HMI, as well as their hardware to match all of this. The PLC and HMI were completely redesigned in new software to accommodate the original functions of the line. The data files were then moved to an easy one-location server for any hotfixes that may occur. All the components were installed on site and tested, and the line now runs more efficiently and at a reduced cost from before. Is there any questions? Yes.
This may be beyond the scope of your project, but why would they replace everything except the field devices and then have to get those Genius boxes to, maintain all the old I/O?
All of their old I/O was actually fast enough for this project, so rather than spend all of the money to replace all of these field modules, they chose to use the Genius buses because it was much less expensive. Some of these devices that they were using were over $1,000 a piece, so rather than spend that money, they chose to use these Genius buses to simply convert that.
And a second question, how many total I/O points are there on this project?
Total I/O points, I'm not totally sure. That was through the PLC. That was not my direct involvement in this project. Yes?
So Logan, what percentage of your time do you spend this semester on this project versus the summer?
Versus the summer? My entire summer I actually spent as an intern at Flanders, and this was my project over the summer. So this semester was more or less getting this presentation ready, getting my report ready, and then doing a few follow-ups actually out on the site as problems arose.
I have a follow-up question.
Yes.
How much time did you spend at this undisclosed location preparing yourself for your particular task? That is, before you actually began your task, how much time did you spend there?
We made 3 site visits. The first was just to see what the line was as it originally existed, to check all of the HMIs to see that they were all working properly. We spent a full 8-hour day there for that. The second visit was actually to see what they would be replacing. So So they brought in all of their hardware that they would be connecting and showed us all of the connections that would be done. That was a half day. And then we went out a third time before installation of this. They actually installed all of the hardware that would be the replacements, and we were sent out to check and make sure that they were all connected properly.
Any other questions?
Yes.
What fraction of the time you work on design of the HMI?
The design of the HMI, as an entire scope of the project, or
Yeah.
I had a total of 3 months designing the entire HMI. This is from getting the screens that they say exist currently on it, looking through them to figure out what differences I had to make to meet the requirements of other lines on the project, and then designing each of the screens from scratch. So that's roughly 3 months.
Thank you.
Other questions?
Anybody else? All right, let's get them in.